Welcome to this explainer. I am so thrilled you're here today because we're going to decode the absolute fundamental language that computers use to understand the real world. When we think of artificial intelligence or machine learning, we usually picture complex neural networks or, futuristic algorithms. But beneath all of that, the actual engine driving these technologies is a mathematical framework that's been around for centuries, linear algebra. In this explainer, we're going to see exactly how this field of math acts as the ultimate translator between our messy physical reality and the precise, structured world of data. It really comes down to this one profound question. How do algorithms translate our completely messy, chaotic reality into actionable predictions? It's really easy to think of linear algebra as just abstract math you might have learned in a classroom, filled with arrows and endless equations. But I want you to shift your perspective today. Think of linear algebra as a bridge. It's the literal mechanism that allows a machine learning model to take something as insanely complex as human behavior, geographic locations, or genetic expressions, and turn them into a format that a computer can actually learn from. So here's our roadmap for today's explainer. We'll be covering translating reality into data, solving systems of equations, understanding vector spaces, linear independence and redundancy, finding the basis, and finally, matrix rank and machine learning. Let's get right into it. Section 1, translating reality into data. We're looking at that crucial first step where messy human concepts become structured numbers. Take a look at this sample human resources data set. To us, right, this represents real people, employees with ages, locations, and salaries, complete with all their messy human quirks. But a computer, it doesn't see a quirky person at all. It just sees a row of carefully scaled numerical features. Notice how the geographical locations are plotted as degrees of latitude and longitude, and salary is in thousands. This conversion is absolutely crucial. To feed this into a machine learning algorithm, we have to strip away the human context and represent each individual as a pure mathematical point in space. And that actually brings us to the foundational vocabulary of this math. A vector is really just that single data point, a d-dimensional array of real numbers. So in that HR table we just looked at, one employee's entire profile, that's a single vector. A matrix, on the other hand, is a structured collection of those vectors, basically the entire HR database. You can kind of think of vectors as the nouns and matrices as the verbs or the structures of our machine learning language. It's this exact setup that allows us to use array operations on computers to process massive amounts of information efficiently. Section 2, solving systems of equations. Now that we have our matrices, what are the actual rules of the game? So, the whole point here is that we use these matrices to perfectly balance real-world constraints. Check out this quote from our sources detailing a classic business problem. Imagine a company producing different products, and each one requires specific amounts of various resources. The goal is perfect resource allocation, right? Finding an optimal production plan where every single unit of available resource is utilized perfectly, with absolute zero waste. Because honestly, a business's worst nightmare is leftover wasted resources. This isn't just an abstract puzzle, this is exactly why we care so much about systems of linear equations. Here's exactly how that factory problem translates into math. You're looking at a system of linear equations. Those x variables, they're the unknown quantities of products we want to make. The a coefficients are the resources required for each product, and the b values on the right represent the total resources we actually have available. By structuring this as a matrix equation, which is often written really compactly as a times x equals b, we can use linear algebra to literally solve for x. It's a perfect, totally logical balancing of inputs and outputs. Section 3, understanding vector spaces. Now we need to understand the playing field where these solutions actually live. A massive idea in mathematics is this concept called closure. Basically, a vector space or subspace must be closed, meaning if you take any vectors in that space and add them together or multiply them by a scalar, the result literally has to stay inside that exact same space. Look at these examples in a 2D plane. Shape A, the square, is definitely not a subspace, because if you scale a vector inside it up enough, it just bursts right out of the box, violating closure. Shape C also fails, because adding a vector from the top wedge to the bottom wedge results in a vector totally outside the shaded area. Only shape D, the simple origin point, and a line passing straight through the origin would actually qualify as true, valid subspaces. Section 4, linear independence and redundancy. Let's shift our focus to efficiency and tackle the huge problem of redundant data. Okay, imagine you're in Nairobi, Kenya, and you're trying to give someone directions to Kigali in Rwanda. You could say, go 506 kilometers northwest to Kampala, and then 374 kilometers southwest. Those two directions, those two vectors, are completely essential. You cannot describe the southwest movement using only the northwest movement. They are linearly independent. But if you then added, oh, and by the way, Kigali is about 751 kilometers west of Nairobi, that third statement, while true, is completely redundant, and honestly just annoying to whoever is driving. You could have figured that out just by combining the first two vectors. So let's formalize this. Linearly dependent vectors contain redundant information. If a set is linearly dependent, at least one vector is just a combination of the others, like that totally useless west vector on our map. But on the flip side, linearly independent vectors possess absolutely zero redundancy. Every single direction is totally essential. Why does this matter to us? Well, because machine learning algorithms absolutely hate redundancy. Feeding a model highly correlated or linearly dependent data completely wastes computational power and can actually end up confusing the algorithms. Section 5. Finding the basis. So how does a computer actually strip away all this redundant information? Think of a basis as the absolute holy grail of our vector space. It is the core vocabulary of our data. Technically, a basis is a minimal generating set, meaning it contains the absolute fewest possible vectors needed to describe every single point in that space. It's also a maximal linearly independent set, meaning if you added even one more vector to it, boom, you'd introduce redundancy. The number of vectors in the spaces literally defines the dimension of the space itself. And computers? They have a super systematic way of finding this basis, using an algorithm called Gaussian elimination. Step 1. You take all your messy, potentially redundant data vectors and just write them as columns in a matrix. Step 2. You apply elementary transformations, like adding and scaling rows, to simplify the matrix into what's called a row echelon form. Step 3. You look for the pivot columns. The original vectors that correspond to those pivot columns, they form your basis. The algorithm systematically crushes down the data, filtering out all the noise and redundancy to leave only the absolute essential directions. Section 6. Matrix rank and machine learning. Let's bring everything we've talked about together right here. The huge concept we've been building towards this whole time is called rank. The rank of a matrix is simply the number of linearly independent rows or columns it contains. And what's really fascinating here is that the row rank always equals the column rank. Rank is the true measure of how much raw, unique information a dataset actually holds. If a dataset has full rank, every single feature is providing totally unique information. But if it's rank deficient, it means there's hidden redundancy. Think about it. A dataset might have 100 features, but if its rank is only 10, there are really only 10 independent dimensions of actual information in the whole thing. This is exactly how we use these concepts in modern AI. Because we understand basis and rank, we can deploy powerhouse techniques like principal component analysis, or PCA. PCA uses these exact linear algebra tools to find a totally new basis for our data, one that captures the maximum amount of variance or information. We can then project our original, massive, high-dimensional dataset onto a much lower dimensional subspace. We compress the data, making calculations way faster and models more robust, all while totally preserving the central story the data is trying to tell us. So, as we wrap up this explainer, I want to leave you with this one thought. Every single time you browse the web, use a map, or stream a video, you are generating massive vectors of data. But how much of that is redundant? How many true hidden dimensions of data are you actually generating every single day? And how might the AI systems running our world be using the elegant rules of linear algebra to compress and make sense of your digital footprint right at this very moment? It is so fascinating to think that behind the magic of AI, it all really comes down to translating our messy reality into the beautiful, structured language of vectors and matrices. Thanks so much for joining me on this deep dive into linear algebra.